那个道啊，不是用知识能够在那边分析的。
Hello everyone. Today we are going to derive the Maxwell equation. We are going to derive the transverse electric fields and also the longitudinal electric fields according to the Maxwell equations. So to begin with, we assume the direction is the direction of propagations. And at the end, we are going to come up with this set of formula. And they are going to be very useful for analyzing the TM modes and TG modes. And the other set of equation and this set of equation will be useful for the TEM mode. And all these equations will be usable in a guided or unguided media. Okay? So the objective of this note to express the transverse based in terms of longitudinal components. And based on the transverse waves and the longitudinal waves, we are going to generalize the methodology for solving the TEM modes, the TE modes, and TM modes in the guide and unguided media. So before doing anything, right, let's come up with some derivation first. Sorry, the definition first. The transverse wave is the way where the direction of oscillation is perpendicular to the direction of propagation. On the other hand, the longitudinal waves are the wave with the directions of oscillation parallel with the direction of propagation. Okay? So now let's recall what we have learned in Maxwell equations. If we are dealing with a sourceless medium, so there will be no current, no charge. Then we will have this set of Maxwell equations. The first one is represents the Gauss's law. The second one represents the Gauss's law for the magnetic medium, for the magnetic field. And these ones came from Faraday's law. And here, we are going to replace the time derivative with j omega. So we get minus j omega mu h. And for exactly the same reason, the last Maxwell equation, which was what originated from Ampere's law. And we are going to use the time derivative. Replace the time derivative with j omega. So we end up with this equation. Okay? So Faraday's law and also Ampere's Maxwell law. So if we explain the equation for Ampere's Maxwell law for A, so we will get this. So the left-hand side represents the determinant forms of the Laplace equations. Log Laplace, the curl, and the right-hand side is just the J omega and then the electric field in three-dimensional space in vector forms. So now if we decompose these determinants, you will get this. And now you have an equation, and the equation have x hat, y hat, and z hat on both sides of the equation. So what we need to do is to equate the coefficient for x hat and y hat and z hat for the whole equations. So this is what you can get. So for x hat, you get this set of equations. For y hat, you got this set of equations. And for z hat, you got this set of equations. And this page is about the derivation for the for equation for A, Maxwell, Ampere Maxwell law. But we haven't done anything for the Faraday's law, so this is the next step. So Faraday's law, so we are going to expand equation 3a, and as we decompose as we represent the curve in determinant form, and we get this, and the left-hand side of the equation is just the right-hand side of the equation is just like this. So again, we can just decompose these determinants form in the plane equations, and we do. Then the next thing that we are going to do is to equate the coefficient for x hat, y hat, and z hat. Yeah? This is really z. Yeah, I make a mistake. And we get this, and we get this. Yeah? So here is z hat. Yeah? This is my mistake.
Supreme Master Ching Hai.
So now we have altogether 6 differential equations.
More about her compassionate life and teachings, please visit
and now, assuming that the wave is propagating in the positive z direction, the amplitude of the wave should be associated with a factor of exponential to the power minus gamma z, where gamma is the propagation constant for the wave in the positive z direction. So literally, we are assuming that the wave can attenuate. We may not be in a lossless medium. So this is the representation of the electric field in the x direction. And we have the amplitude here, E of x0 is the amplitude, and we have the exponential expression here, and this represents the unit vector.
Go to suprememastertv.com.
And in the lossless medium, then you can do this,
that is for your device.
or you can just assume that
Android phone or tablet.
this thing is just minus k of z.
And any other device. Under that, you can click
So
on the
if
plus
you
screens buttons for
differentiate
Each
this
Max screen
with
has a
respect
nearly
to
infinite number of screens behind it. 1 plus 119,200 max.
Z,
Watch one big screen of Supreme
then you
Master
will get
TV
this.
with a thin line of 119,200
And
screens
if
of
you
Max surrounding,
differentiate
along with
this
additional
one more
smaller
times,
screens. The most powerful daily prayer can be viewed similarly with
now
Max screens
from
surrounding
here,
it.
if you
Combo.
both
See
sides of the
Supreme
equation
Master
have
TV alongside 3 or more
e of
smaller
x,
screens of Max.
so it
Enjoy
can be
our
cancelled
TV
out.
and the
So
immense blessing at the same time. The download button downloads
we
a
find
video
out
or audio file of the most powerful daily
the
prayer to your device to keep the positive energy
puzzle
flowing
Z
without an
notation
internet
is
connection.
equivalent to
Please tell all you
minus
know
J
all
of
others,
K,
so this can help the
J
whole
times
world
K of
be
Z.
saved. Print out a Supreme Master TV Max card to distribute wherever you
And
go. For example, if
yeah,
you
this is
visit
the way how we continue with our analysis. So we replace all the puzzle Z with minus J of K. And what we got is like this. From equation 1C to 2C. We got this.
And more abundant blessings in our life. Just try it. And
Now,
see the miracles that will happen.
let's do this. So if we replace, now here we have a puzzle Z notation in this equation. So we replace it with minus J of K. J of KZ, yeah, precisely. J of KZ. So we get this. And similarly, we can do the same for this one.
Number 64 of many and counting.
And similarly, we can do the same for this one. And similarly, we can do the same for this one. Sorry, this one.
etc.
Sorry, this one.
February 2024.
And we can't do anything for the equation without any puzzle Z notation. So such as this one, we can't do anything. And this one. So we just copy down. Yeah. And same for here.
By creating peace, we all can make a loving, serene, and prosperous world.
So now, basically, most of the things have been done. The next thing is to
lean on and give thanks to the reunited three most powerful always. God, Timko 2, and the Son of God.
Express the transverse wave components instead in terms of longitudinal components. So these are the equations that we have derived so far. This was from previous page. So now what we can do now is we need to do a lot of algebra manipulations here. For example, the first step, what you can do is to pay attention to equation 5b and 6a. In equation 5b, we have h of x. Similarly, in equation 6a, it also has h of x. So what we can do is to eliminate either h of x or e of y. And now we can try this. And we eliminate e of y.
Truth-seeking viewers, we thank
So
you for your company for
we
today's
can
episode
do the
titled
same
The Love
for
Devoted
equation
Group
7.
of Practitioners, Part 3 of 11. On
We
between
can
Master and disciples.
further simplify
Up next,
equation
we
7.
have Veg News 24 most popular
So we do this.
recipes of 2024.
You have to do it very
10
carefully.
gluten-free
Otherwise,
vegan
it's very
lasagna
easy to
and
make a
no-bake
mistake.
vegan chocolate espresso caramel
And
bars right after Noteworthy News. Please
then
stay
we
tuned
just
to Supreme
do
Master
one
Television
more
for
step
more
of
constructive
algebraic
programming.
manipulation, and you will end up with this
Being
expression.
vegan, having peace, heaven, Godspeed.
And what we are going to do is to further simplify this.
Free international vegan recipes?
And we copy
Log on
the
to suprememastertv.com
original equation 5 and
/vegan
6 again.
recipes.
And then we multiply both sides of the equation by j omega. And we get this. And now, let's define. We have a propagation constant, a wave number known as cutoff wave number, and this is equal to k squared minus k of z squared. So literally, this term, we are going to replace this with k of z squared. So as you do that, then we will come up with a very clean equation. And this will be one of the equations to express the transverse magnetic field in terms of the longitudinal component. Longitudinal in the sense that they are in the direction of z. So similarly, we can do the same for equations 6b and 5a, but this time we are going to eliminate
May heaven bless your noble endeavors and protect you always,
I think
especially while on challenging
xy. Yeah, exactly. XY. I got it written incorrectly here. Yeah, it should be XY. And now we are going to express the h of x in a similar manner. And we are going to substitute this to equation 6a, and we get this.
Great job keeping your mama safe, little one.
So E of I has its own expression.
Thank heaven for
there will be there's a lot of algebraic manipulations here. So similarly, we can express E of x in a similar manner.
For the awe-inspiring and majestic sceneries, and for all the amazing people from the animal kingdom, our co-inhabitants, that generously share their beauty and unconditional love.
And substitute E of x into 5a, which will end up with the magnetic field in the y direction, h of y, and we will get this, and we can do the same for all other components. So as a result, we will get a very, very shortened set of formula for the transverse field components. And this transverse field component will be expressed in terms of the longitudinal field components. And all these components are based on equation 5 and equation 6. They are derived from equation 5 and equation 6. So now you might wonder, well, how are we going to use it? First of all, in the electromagnetic wave, we have two classes of, we have different modes. One is so-called transverse electromagnetic modes, And this mode is very similar to the light that we can see in the daytime. They have low longitudinal components. So in this case, E of x is E of z and x of z is 0. So if you substitute E of z being 0 and substitute h of z equal to 0 into this set of equations, you will end up with nothing. So this set of equations are not intended for TEM modes, transverse electromagnetic wave. So what about this set, the original set? Yes, the answer is yes. So if you substitute h of z with 0 here, then you will still get the equation, and this equation will be highly useful for you to further derive other parameters, say impedance, wave propagation constant, wave number, for example, and the same for E of z. You can do that. So let's take a look on the example. So now E of TEM mode. In TEM mode, there will be low oscillating components parallel with the direction of propagation. The direction of propagation is z. So Z of z is 0. H of z is 0. And this is a definition of transverse electromagnetic modes in mathematical forms. So let's try. We bring up the whole set of equation 5 and equation 6 here, and we substitute h of z equal to 0 and E of x equal to 0, and see what we can get.
Where the festivities of the annual Monaco National Day are enthusiastic, coordinated through widespread community participation with
so the first one, this one will be 0. The second one, this one will be 0. The third one, we can't do anything. The equation 6a, we can do this. This one will be 0, so we end up with this one. And this one, we can do something for this. Yeah? This one, E of z, is a longitudinal component. So we can delete it. So this is what we can get. This is the governing equation for TEM modes.
Uplifting news for a caring world. Supreme Master Television brings you relevant news from around our beautiful planet 24 hours a day, 7 days a week.
If we multiply equation 19, the last two equations, if we multiply these two equations together, and let's see what we can get. So we multiply these two together, and remember, E of x divided by h of y is equal to the intrinsic impedance, which is given by square root of mu divided by epsilon. So we can get this, and as you know, right, if you move those mu and epsilon to the right, then we get k squared. So here it's very clear for TEM mode, the wave vector is exactly equals to the wave number is exactly equals to the longitudinal wave number. So in this case, we can conclude that there is no cutoff frequency. There is no cutoff in TEMO. So no matter how low the frequency you are dealing with, the mode will, the electromagnetic wave will pass through. It doesn't matter whether the electromagnetic wave is 1 or 2 kilohertz or 1 or 2 gigahertz or 1 or 2 terahertz. It doesn't matter. The propagation, the cutoff frequency, there will be low cutoff, so you will propagate. So the conclusion at this stage, the cutoff wave number is 0.
Our programs offer many languages. Please
And there will be low cutoff frequency. Now let's take a look in other parts. Now let's look at the Helmholtz equations. This is the original form of the Helmholtz equation, and we are going to do this. And remember, as before, this one can be substituted with k of z. But k of z times k of z is equal to k squared. This has already been proven in the previous page. You know? So in this case, when you further derive the Helmholtz equations, you will end up with this, and the Laplacian operator will have only two components, and this is also so-called del of t squared. So these are the differential equations that you will be required to solve in TMO. And you can substitute whatever you like here. And TEMOs has been done. Now let's take a look in TEMOs. Normally, these modes occurred in a guide medium, a confined medium, like waveguides, dielectric waveguide, optical fibers, parallel phase. So let's take a look. So we are going to recall equation 18. We are not going to use equation 5 or 6. In this case, luckily, we have already expressed the transverse wave component in terms of the longitudinal wave components. Say, for example, when we deal with TE modes, by definition, TE modes is the mode with low longitudinal electric field. So E of Z is 0. You only have transverse electric field. You don't have any longitudinal electric field. And in this case, the only longitudinal component is H of Z. So let's try this. We will have this, and what we can do is substitute all this equation with E of Z equal to 0 and see what we can get. Say, for this equation, we get this. Yeah, this one becomes 0. And for this one, we can do the same. And for this one, we can do the same. And for this one, we can do the same. So these are the formula for TG modes. And hence, the transfer components depends on H of Z. And the Helmholtz equation is like this, so there's no way to further simplify it. And similarly, for TM modes, we can do something similar. First of all, we need to identify what TM modes means. Transverse magnetic modes means the longitudinal magnetic modes is 0. So in this case, the only thing that we have left for the longitudinal direction is E of Z. Again, we bring up all the, we call the equation
Up next,
18. So what we need to do is to substitute H of Z being equal to 0 to all of these equations. This one, this one, this one, this one. Then we will get this. Yeah, this one.
We'll return with more meaningful news here on Supreme Master
This one.
Television.
This one. And hence all the transverse wave component depends on E of Z, and we can solve the equation for this. So this will be the governing equation for the electric field for TM modes. I think that's the end of the presentation. And if you have any question, please leave your question to the comment section of this video. Thank you. Bye-bye.
Best utilize this free of charge tool. Easy. Play it on as many devices as